modern science explains the origins of the universe within the Big Bang theory. According to this theory, the universe arose from the explosion of the singularity. The singularity is a point in the fabric of space and time where the concentration of energy and matter becomes extraordinarily high, reaching almost an infinite level, while the spatial and temporal dimensions are reduced to near-zero values. However, recently the James Webb Telescope has made a bold announcement that the universe has existed uninterruptedly and that the Big Bang theory is wrong in its approach. If you're interested in keeping up to date with news from the universe and its surroundings, subscribe to our channel, hit the like button, and turn on the notification bell. The concept of singularity describes a state where neither time, space, nor matter existed. The question that arises is where this singularity came from, what preceded it, and what even triggered the event that culminated into the Big Bang. It is debated whether the universe has existed eternally or whether it had a definite starting point. The singularity that preceded the Big Bang event contained the entire mass present in the universe, and this resulted in the complete suspension of the flow of time. This aligns with the perspective proposed by Albert Einstein, which suggests that debating what happened before the Big Bang is meaningless, since the notion of a before had no place. The idea that the universe is not expanding in empty space may be difficult to conceive. This conception is based on a theory known as the Einstein theory of general relativity, which he developed in 1915, and which remains to this date our best description of space and time. This theory is the foundation for many of these interesting and peculiar ideas. The theory of general relativity is supported by evidence such as the expansion of the universe, which was discovered by American astronomer Hubble in 1929. In addition, there is the cosmic microwave background radiation, which is uniformly distributed throughout the universe and was discovered by the American scientist Spenzias in Wilson 1965. The discoveries support the basis of our current understanding of the evolution and the nature of the cosmos. This radiation emerged approximately 379,000 years after the Big Bang, in a period known as the hydrogen recombination era. According to the Big Bang theory, in its earliest moments, our universe was tiny, no bigger than an atom. In times past, the notion of nothingness was a sustainable state. Asking how long it lasted is irrelevant, since during this period the concept of time simply had no existence. In this era, our world emerged from a random quantum fluctuation that emerged from the void, which represents a significant level of depth. Perhaps a question of greater relevance might be whether this quantum fluctuation was truly random, as Einstein famously put it in his famous phrase, "God does not play dice." With this notion in mind, it is interesting to reflect on the implications of this. What prevents another small fragment of energy-filled void from appearing again, leading to a new Big Bang? There is a possibility of this occurring with a 100% probability, which could annul the existence of mankind. In the multiverse theory, the emergence of life occurs through a natural phenomenon in which universes with parameters conducive to more black holes will have a greater chance of generating offspring, thus increasing the probability of life being present in those universes. Recently, renowned physicist Brian Cox explored the fundamental question of how the universe began. Cox presented the Big Bang theory, but in return, challenged the conventional perspective by introducing a fascinating approach, the idea of the existence of a time before the Big Bang. This intriguing notion expands our understanding of the origins of the universe. The notion of a pre-Big Bang universe connects to the theory of cosmic inflation. According to this theory, the universe underwent an exponential expansion in an extremely short period after the Big Bang. This significant growth allowed the universe to become uniform indeed, explaining its observed homogeneity on a large scale. Although inflation remains a fundamental part of the prevailing cosmological model, Koch's idea of a pre-Big Bang state adds a layer of complexity to the chronology of the evolution of the universe. One question that arises is what could have caused this primordial energy to trigger such a sequence of events? Could it be the result of interactions between forces that we do not yet fully understand? Koch's ideas about the time before the Big Bang are supported in the work of Roger Penrose, an outstanding mathematician and physicist who was awarded the Nobel Prize in Physics for his contributions to the understanding of black holes. Although his focus is on black holes, Penrose also introduces the concept of eons, which occurs in a cyclic framework. Each eon begins with a Big Bang, followed by a period of expansion, contraction, and finally a big crunch, in which the universe returns to its original state. This cyclic cycle sets the basis for a new eon, perpetuating itself indefinitely. Penrose's eon theory revolves around black holes, celestial objects of enormous gravitational force that emerge from the collapse of massive stars. Over time, these black holes evaporate through Hawking radiation, releasing energy. Penrose speculated that dead black holes from earlier eons may still exist today, leaving possible imprints in our observed universe. These remnants Penrose called Hawking points, in honor of Stephen Hawking and his contribution to the understanding of Hawking radiation. The late physicist Stephen Hawking's proposal could offer clues supporting the existence of states prior to the Big Bang. Roger Penrose's idea of Hawking points could represent a potential clue to the existence of a pre-Big Bang universe. These enigmatic points, which are about 8 times to the size of the Moon, refer to slightly warmer areas in the sky that can be detected by advanced observational techniques. While Hawking's concept of the dots stands out in the scientific conversation and highlights the fluidity of our understanding of the beginnings of the universe, the discussion also highlights the importance of scientific exploration and the potential for paradigm-shifting discoveries in the future, as with any revolutionary scientific proposal. Brian Cox and Roger Penrose's exploration of a time before the Big Bang faces challenges and controversy. Critics argue that the concept of a pre-Big Bang universe remains speculative, as it lacks direct observational evidence. In addition, the cyclic nature of Penrose's eon theory raises questions about the conservation of energy and the ultimate fate of the universe. Some skeptics question the feasibility of an infinite cycle of eons, as this could conflict with the laws of thermodynamics and other fundamental principles of physics. Now let's delve into another related theory, the multiverse hypothesis in cosmology. This notion suggests the existence of multiple universes, each with its own physical laws, constants, and properties. Well, the basis of this idea lies in the belief that our universe could be one among many in a vast and diverse multiverse. The concept of the multiverse has gained momentum as a way to explain certain aspects of our universe that seem to be finely tuned for the existence of life. Scientists have observed that the fundamental constants and physical laws governing our universe appear to be carefully balanced to allow the emergence of life as we know it. From this observation, some have proposed the anthropic principle, which holds that our universe has the characteristics it does because it must be capable of hosting intelligent observers like us. And well, let us know your opinion in the comments box. If you liked the video, remember to like and subscribe, and I'll see you in the next one. Thank you so much for watching.